Welcome back, everyone. Today we're unpacking one of the most famous and honestly, maybe the most frustrating ideas in all of modern physics, string theory. For decades, it was basically treated as gospel, hailed as this ultimate theory of everything. But as we're going to see on this explainer today, string theory is actually going through a massive, dramatic shift. It is morphing from this dogmatic, overarching theory into something entirely different, a stripped-down, super practical tool. So let's dive right in and see how an idea that literally promised us the universe is finally finding its footing by going way back to basics. So here's the massive puzzle we really need to untangle today. How exactly did this incredibly ambitious theory, an idea that was supposed to describe every single particle in existence, and finally marry the messy world of quantum mechanics with the vast forces of gravity, how did it become something that is, mathematically speaking, absolutely beautiful, but totally unreachable by actual experiments? You know, it's that classic story of a brilliant idea just getting a bit too big for its own good. But more importantly, we're going to look at how physicists today are trying to sieve it from itself.
All right, let's kick things off with Part 1, the theory of everything. To really get where string theory is heading, we have to look at how innocently it all began. Back in the 1960s, this Italian physicist named Gabriele Veneziano used some basic principles and particle collider data to come up with a formula that perfectly captured how elementary particles behave. Pretty cool, right? Well, fast forward to the 1970s, and physicists realized that Veneziano's math actually described particles not as tiny little dots, but as incredibly small vibrating strings. Think of it like playing a guitar. Different notes come from strings under different tensions. And by looking at particles this way, physicists realized they could just sidestep all those massive mathematical headaches that normally ruined any attempt to merge quantum theory and gravity. Suddenly, the dream was born. One magic formula to explain literally everything in the universe.
But then came the bloat. As researchers pushed the math further and further, the theory got wild. Incredibly complicated. To make the math actually work, they realized these strings had to exist in at least 10 dimensions. Yes, 10. That's our 4 familiar dimensions of space and time, plus 6 completely invisible ones that are supposedly curled up so tightly we can't even perceive them. And if keeping track of 10 dimensions doesn't make your head spin, the math also required all these symmetries we've never actually seen in nature, and it permitted this unimaginably vast number of possible universes. It was getting completely out of hand.
Which leads us perfectly into Part 2, a beautiful, untestable mess. Here is the harsh reality. These theoretical strings, they are simply too small to ever probe directly with any technology we can even conceive of right now, which makes the theory basically impossible to falsify. And man, the pushback from some corners has been fierce. Take Peter Woit, a mathematician over at Columbia University. He is a very hardened critic of string theory. And he frankly says, it's just not science. It's a really insane situation. Woit and other critics argue that because you can't actually prove it wrong, string theory has been adopted with almost a blind tribal allegiance rather than real rigorous scientific skepticism.
And that hits the nail on the head regarding the central problem. There's this huge gap between the initial promise of the theory and its actual execution. Look, even the physicists who use these mathematical frameworks every single day openly admit how frustrating this is. Clifford Chang, a physicist at Caltech, freely admits that string theory has totally failed to give us a working theory of the actual physical world we live in. And remember, that was the entire point of the theory to begin with. It's a tough pill to swallow. But Chang and others say, hey, this doesn't mean the theory is worthless. It just means our approach has to change.
So how do you fix a bloated, totally untestable theory? Well, you strip it down to the absolute studs. Welcome to Part 3, the bootstrapping revival.
This is a completely unexpected pivot happening in physics right now. It centers around something called the bootstrap philosophy. Basically, bootstrapping means building up explanations from a tiny, super consistent set of general principles. You do this instead of trying to force your laws down from some massive, overarching framework. Chung puts it perfectly. He says it's moving away from the old mindset where a brilliant physicist essentially comes down from the mountain with a specific, rigid model carved on stone tablets. Instead of treating the theory like handed-down gospel, they are throwing out the bloated models and starting over from the absolute basics. Let's look at exactly how they're doing this. Step 1. You start with incredibly conservative assumptions, like assuming that if you add up the probabilities of every possible outcome of an event, it has to equal exactly 100%. Step 2. Assume the laws of physics stay consistent for observers moving at different speeds. These are rock-solid basic principles of physics. Then, step 3, you apply those constraints, turn the crank on the math, and simply observe what kinds of theoretical models naturally emerge. You aren't forcing a predetermined model on the math. You're literally just seeing what the math builds from the ground up.
But, as you might guess, this new methodology has sparked a fiery debate of its own. Let's get into part 4, a circular argument? To really understand this debate, we need to compare two fascinating brand new studies from January that both use this exact bootstrap method. One study was led by Clifford Chung's team. They started with those basic rock-solid assumptions we just talked about. But then they added one extra unproven mathematical constraint called ultra-softness. That's basically the idea that the probability of certain particle interactions just drops off at high energies. Now, totally separately, a study led by Henrietta Elvang at the University of Michigan used the basic constraints, but her team added something called supersymmetry, a hypothetical maximal coupling between matter and forces. So, two distinct teams with two completely different sets of added constraints. And here is where things get absolutely wild. The inevitable mathematical result of both of these independent studies, both groups concluded that the absolute only theory that could satisfy their specific, rigid assumptions was a theory that looked exactly like string theory. Yep, even starting entirely from the bottom up, the math pointed them right back to the exact same framework they were trying to evaluate in the first place.
Now, for the critics, this is a massive red flag. Peter White points out that there is currently zero physical experimental evidence to justify throwing in special assumptions like ultrasoftness or supersymmetry. He essentially accuses these efforts of intense circular reasoning, arguing that there's absolutely no reason to add these assumptions, quote, unless you want to get string theory to come out of it. And honestly, it's a valid structural critique. If you deliberately bake string theory-friendly ingredients into your starting assumptions, well, you really shouldn't be surprised when you pull a string theory cake out of the oven.
But let's look at the pragmatic defense here. Clifford Chung pushes back against this criticism pretty hard, famously saying, I don't have a dog in the fight, I just work here. What Chung and Elvang are heavily stressing is that they are absolutely not trying to prove that string theory is inevitable. That's not the goal. They're just exploring the mathematical space of what's possible under really rigid constraints. They are literally just following the math wherever it leads them, regardless of whether those initial constraints match our current reality. So, what does this all mean for us? How does this highly abstract math translate into real physics? Let's bring it all home with Part 5, Building Better Toy Models. Henrietta Elvang explains this brilliantly. We have to recognize what these equations actually are. They are not perfect representations of reality. Instead, they're what physicists call highly controlled toy models. By using this bootstrap method, physicists get a safe, controlled sandbox. It lets them meticulously build and test their mathematical tools. And the hope is, once those tools are perfected in the sandbox, they can finally let go of the rigid, unproven assumptions and try to build up toward actual reality. And the value of this whole pivot is huge. It's all about finding a backdoor to real predictions. Theoretical physicist Renaud Alal notes that quantum gravity desperately needs reality checks. We need actual experiments and numerical simulations. Researchers like Andrew Tolley are hoping this bootstrapping effort might actually inspire those very experiments. See, because some of these bootstrapping assumptions tie together particle behavior at different energy levels, physicists can potentially use low-energy physics, which we can totally test and elaborate now, to infer things about high-energy physics, which we can't test. It's an incredibly clever way to finally make testable predictions. But perhaps the absolute coolest takeaway is this. This bottom-up approach acts as a literal blueprint for finding alternatives. Chium points out that the field of string theory has been, well, kind of culturally toxic lately. People either dogmatically defend it or they completely give up and walk away. But by exploring theories agnostically from the bottom up like this, we are mapping out exactly what mathematical ingredients are required to build a working universe. So if you hate string theory, fine. This method tells you precisely what alternative constraints you need to go find to build a viable replacement. Which leaves us with this final, thrilling question to ponder. What new alternative models will finally emerge from this effort to potentially replace string theory? By letting go of those old, empty promises and returning to first principles, physicists might have just found the key, not necessarily the key to proving string theory right, but the key to finally unlocking the true, testable mechanics of our incredible universe. Thank you so much for joining me on this explainer today. Keep asking those big questions, and I'll catch you next time.